Welcome to Poddy, May 10th, 2026. A deep dive in... Here's a question that should make every security engineer a little uncomfortable. What if the hardest bugs to find, the ones that have survived decades of expert review, are actually easier for AI to find than they are for humans? Because that's not a hypothetical anymore. An AI model just dug up a 27-year-old vulnerability hiding inside OpenBSD, one of the most security-conscious codebases on the planet, and it did it for $20,000. That number is the whole story. Not because it's cheap in absolute terms, but because of where that price is going and how fast.
Okay, so I want to make sure I understand the stakes here before we get into the mechanics. When you say a 27-year-old vulnerability, you mean this bug was sitting in production code in a security-focused operating system for nearly 3 decades and nobody caught it? Like, through all the audits, all the expert eyes, all the CVE research over the years, it just survived? That feels like the kind of thing that should shake people's confidence in how we've been doing security.
That's exactly the right reaction, and that's exactly the tension we're going to sit with for the next 12 minutes. Because yes, OpenBSD has mandatory code auditing. It's the project that basically invented the modern security-first development culture, and this bug's still hidden there for 27 years. So today, we're going to unpack 3 things. Why AI changes the economics of vulnerability discovery in a structurally fundamental way, what the people building defenses are actually doing about it, and, maybe most importantly, what happens when AI is simultaneously finding old bugs and introducing new ones through what's being called vibe coding. That last one is the part that doesn't get enough attention.
Right, so let's build the foundation here because I think a lot of listeners might be coming in with a vague sense that AI and security are colliding, but the mechanism isn't always clear. Can you walk me back to how vulnerability research actually worked before any of this AI stuff? Like, what does a skilled human researcher actually do when they're hunting for bugs in a codebase?
So let me think about the best way to frame this. Traditionally, vulnerability research is brutally labor-intensive. A skilled researcher might spend weeks or even months on a single target, reverse engineering binaries, reading through thousands of lines of source code, fuzzing inputs to see what makes the program behave unexpectedly, and then manually reasoning about whether an unexpected behavior can be turned into an actual exploit. The key thing to understand is that finding a bug and weaponizing it are 2 very different skills. Chaining 3 to 5 separate weaknesses into a working exploit sequence. That's the part that requires the deepest expertise. And that expertise is rare and expensive. The asymmetry between offense and defense has always existed. Attackers only need to find one flaw. Defenders need to close all of them. But historically, that asymmetry was bounded by human labor costs on both sides. What LLMs do is break that bound.
So when you say LLMs break that bound, what's the actual mechanism? Because I can imagine an LLM reading code, but reading code and understanding the subtle interaction between a singly linked list data structure and TCP state management across millions of packets. Those feel like very different cognitive tasks. What's actually happening when an AI model does this kind of security research?
Here's what most people get wrong about this. They assume LLMs are just doing fancy pattern matching, like they saw a similar bug in their training data and they're retrieving it. And that's partly true, but it undersells what's actually happening. These models have been trained on enormous corpora of code, CVE databases, exploit write-ups, protocol specifications. So they've essentially internalized what vulnerable code patterns look like at a statistical level that no individual human could match. But the more important development is that they can now reason about software behavior in a way that begins to approximate expert intuition. And they can do it at machine speed across thousands of parallel runs. The Mythos model from Anthropic, which is the one that found the OpenBSD bug, ran approximately 1,000 scaffold runs to discover that flaw. Each run is the model working through the codebase, forming hypotheses, testing them. No human researcher is running 1,000 independent analyses of the same codebase.
Okay, so walk me through the actual bug, the TCP SACK thing, because I think listeners need to understand what was actually found here. Not just that something was found, like what is TCP SACK and why is a bug in it a big deal? I know TCP is the foundational protocol that basically runs the internet, but the SACK part is less familiar.
Great question, and this is actually a really elegant piece of networking to understand. So, TCP, Transmission Control Protocol, is how data gets reliably delivered across the internet. When you send a large file, it gets broken into packets, and if any packets arrive out of order or get dropped, TCP figures out what to retransmit. Selective Acknowledgement, or SACK, is an extension that makes this smarter. Instead of just saying, I got everything up to byte 5000, SACK lets the receiver say, I got bytes 1 through 3000 and also bytes 4500 through 5000, but I'm missing 3001 through 4499. That hole in the middle, the implementation has to track that state somewhere. And in older code bases, that state tracking happens in data structures like singly linked lists. The bug mythos found lives in exactly that data structure in OpenBSD's TCP SACK implementation, a denial of service vulnerability that's been sitting there for 27 years. And the reason it survived is that this class of bug is genuinely subtle. The flaw isn't obvious from reading any single function. It's in the interaction between how state gets updated and how edge cases in packet sequencing can corrupt that state. That's exactly the kind of multi-step reasoning that exhausts human reviewers.
And OpenBSD of all projects. I want to make sure listeners appreciate what that means. This isn't some random startup's code base. OpenBSD is the project that basically pioneered proactive security auditing in open source. They have a whole culture built around finding these kinds of bugs. So, if a 27-year-old vulnerability survived in there, what does that say about every other codebase that doesn't have that level of scrutiny?
That's the implication that keeps me up at night, honestly. My take is that the OpenBSD finding isn't just a story about one bug, it's a calibration signal. If this class of vulnerability can survive for 27 years in a codebase with mandatory auditing and an unusually strong security culture, then the latent vulnerability inventory in legacy codebases across critical infrastructure, financial systems, industrial control systems, that inventory is almost certainly larger than anyone's current threat model assumes. And the Mythos results weren't just the OpenBSD bug. A related 16-year-old bug in FFmpeg's H.264 slice boundary handling was found for around $10,000. We're talking about mature, widely used open source projects. The performance jump is also worth emphasizing. Mythos achieved a 72.4% exploit success rate and demonstrated the ability to chain 3 to 5 vulnerabilities into working exploit sequences. Prior AI models on equivalent tasks were at near zero. That's not an incremental improvement. That's a qualitative threshold being crossed.
Wait, let me sit with that number for a second. 72.4% exploit success rate. Chaining 3 to 5 vulnerability. That's not just finding the bug. That's building a working weapon. And prior models were at near zero on the same tasks. So something changed fundamentally, not just incrementally. I'm curious about the scaffolding side of this, though. You mentioned 1,000 scaffold runs. What does that architecture actually look like? How do you organize an AI agent to do this kind of research without it just spinning in circles?
So, this is where the finite state machine concept becomes really important, and I think it's one of the most underappreciated ideas in the whole discussion around AI security agents. A finite state machine is basically a formal way of saying the system can be in one of a defined set of states, and specific inputs or conditions determine which state it transitions to next. When you use an FSM as an orchestration harness for an AI security research agent, you're giving the overall system deterministic, auditable logic that constrains what the AI can do at each stage of the workflow. So instead of an unconstrained agentic loop where the model can wander anywhere, you have reconnaissance state, hypothesis formation state, testing state, validation state, and so on. Each transition is governed by defined conditions. The benefit is that the system's behavior becomes more predictable, and critically, the failure modes become more bounded. If something goes wrong, you can actually trace back through the state log and understand what happened. That's a huge deal when you're talking about autonomous systems doing offensive security research.
Okay, so that's the offensive side. AI getting dramatically better at finding and exploiting vulnerabilities. But there's a whole other dimension here that I want to make sure we cover, and that's the defensive tooling response. Because you mentioned IronCurtain earlier, Niels Provos building this open source framework. And Provos is not a random person. Can you give listeners some context on who he is and why his approach to this problem is worth paying attention to?
So, Niels Provos is a veteran security engineer with foundational work on OpenBSD. Yes, the same project where Mythos found the 27-year-old bug, which is a genuinely interesting coincidence. And he's known for pioneering work on honeypots, which are decoy systems designed to detect and study attackers. So this is someone who has been thinking about adversarial security systems for decades. What's notable about IronCurtain is the design philosophy. Rather than trying to make AI models intrinsically safe through alignment training, Provos is building security at the infrastructure layer, treating the LLM as an untrusted component in a larger system with hard policy boundaries. The way it works, based on the reporting, is that IronCurtain routes LLM-generated TypeScript and MCP tool call requests through a trusted proxy policy engine that enforces a user-written constitution. A compiler LLM verifies rule compliance against adversarial test scenarios, and unauthorized actions get blocked or escalated. The framing that keeps appearing in coverage, including a Kaspersky piece and a LinkedIn post about the project, is that this is a security buffer between the AI agent and the systems it operates on.
The Constitution framing is really interesting to me. So you're basically writing down rules in natural language or some structured format about what the AI agent is and isn't allowed to do, and then a separate LLM is acting as a compliance checker against those rules. And there's also this companion tool, Xfire, running 3 independent AI agents in parallel for security code review, deliberately isolated from each other. What's the logic there? Why isolate them from each other's outputs?
The isolation is the clever part, and it's directly addressing a failure mode that most people don't think about. If you run 3 AI agents and let them see each other's outputs, you risk correlated failures. All 3 models might make the same mistake, or the first model's framing might anchor the other 2. By keeping them isolated, you're treating their independent outputs as 3 separate hypotheses, and you only gain confidence when multiple isolated agents converge on the same finding. It's the same logic behind why scientific studies need independent replication, or why financial auditors can't discuss findings before they've completed their own review. My read on IronCurtain overall is that Provos is essentially doing for AI agents what the security community eventually did for browsers. Not trying to make JavaScript intrinsically safe, but sandboxing it so its failure modes are bounded. That's a mature security engineering philosophy. Assume the component will misbehave, design the container accordingly. What's notable is that this approach got enough attention to be featured in Wired, which suggests the security community is taking the infrastructure layer defense model seriously.
I want to push on the asymmetry angle because I think this is the part that really concerns me and probably concerns a lot of security professionals. You've got commercial LLMs that are tuned to refuse requests that look like offensive security work. So a legitimate red teamer or penetration tester trying to use these tools for authorized work faces friction. The model says no or gives watered-down responses. But an adversary using a fine-tuned or uncensored model doesn't face that friction at all. Is that actually the dynamic we're seeing play out?
Yes, and this is one of the genuinely thorny problems in AI safety right now. The guardrails that make commercial LLMs safer for general deployment are the same guardrails that create friction for legitimate defensive use. A pen tester trying to understand how to chain vulnerabilities for an authorized assessment hits refusals. A threat actor using an uncensored model or a fine-tuned variant doesn't. So the safety measures end up being asymmetrically costly. They impose friction on defenders while adversaries root around them. And this isn't hypothetical friction. If you're doing legitimate red team work and your AI assistant keeps refusing to help you understand exploit mechanics, you either waste time on prompt engineering, switch to a less capable uncensored model, or just don't use AI for that part of the workflow. Meanwhile, the threat actor has no such constraint. The $104 million cross-industry defensive initiative that was reportedly triggered by the Mythos findings suggests that major players recognize this inflection point, but institutional response cycles typically lag capability jumps by 18 to 36 months. And that gap is where the real risk lives.
Okay, so I want to make sure we cover the vibe coding angle because I think this is actually the sleeper issue in this whole discussion. Most of the conversation is about AI finding old bugs, but there's a parallel story about AI introducing new bugs. Can you explain what vibe coding is and why the security risk is structural rather than just incidental?
So, vibe coding, the term itself is a little tongue-in-cheek, but the phenomenon is completely real. It refers to the practice of using AI coding assistants to generate production code with minimal human review. You describe what you want. The AI writes the code. You run it. It seems to work. You ship it. The vibe is that everything feels fine because the code runs. The security risk is that AI-generated code can introduce subtle vulnerabilities that aren't obvious from reading the output. Incorrect input validation, improper error handling, insecure default configurations, logic flaws in state management. And here's the structural part. The vulnerability surface is distributed across every codebase where developers are using AI assistants. The code provenance is opaque because there's no clear audit trail of what was AI-generated versus human-written. And the review gap is systematic. This is structurally analogous to the supply chain risks that made Log4Shell and SolarWinds so damaging. In those cases, the vulnerability was buried in a widely used dependency, and the review gap was systematic rather than incidental. Vibe coding creates the same pattern: invisible, distributed, systematically.
And if you put that together with AI-powered vulnerability discovery, you're describing a feedback loop that's almost self-reinforcing. AI coding assistants introduce bugs today. AI vulnerability discovery tools find those bugs tomorrow. And neither pure offense nor pure defense can resolve that unilaterally. That's a genuinely uncomfortable place to sit. If you're watching this in 2025, you're going to look back and remember exactly when this dynamic became visible. And it's right now.
That's exactly the right frame. And I want to make the economic dimension concrete because I think that's what makes this urgent rather than just theoretically interesting. $20,000 to find a 27-year-old 0 day in a hardened code base. To put that in context, 0 days in widely used software can sell on the legitimate bug bounty market for anywhere from tens of thousands to millions of dollars, depending on the target. On gray or black markets, the prices are even higher. So at $20,000 cost, the economics of AI-assisted vulnerability discovery are already favorable for well-resourced actors. The question is where that cost curve goes. And based on the trajectory in the Mythos findings, $20,000 for the OpenBSD bug, $10,000 for the FFmpeg bug, and the pattern of rapid capability improvement in frontier models, one plausible trajectory is that within 18 to 24 months, automated AI vulnerability discovery reaches price points in the $1,000 to $5,000 range per confirmed 0 day. I want to be clear, this is pattern matching from a limited number of data points, not a first principles forecast. But the directional signal is consistent enough that I'd treat it as a planning assumption rather than a tail risk.
At 1,000 to 5 dillies to sip and sober per 0 day, you're not just talking about nation states and well-funded research labs, you're talking about mid-tier threat actors, ransomware groups, even sophisticated individual hackers. That's a massive expansion of the population of people who can do this kind of research. So what's the defensive response? Is IronCurtain and Xfire enough? Is the $104 million initiative enough? What should people actually be watching?
So here's my honest take. IronCurtain and Xfire are important not because they solve the problem at scale, but because they represent the right design philosophy. Infrastructure layer controls rather than model-level alignment. Policy engines as trusted intermediaries. Multi-agent isolation to prevent correlated these are the right architectural instincts. And here's the contrarian take that I think most people haven't fully considered. The IronCurtain architecture, policy engine as trusted intermediary, constitution-based rule verification, multi-agent isolation, looks less like a finished product and more like an early prototype of what may become a required compliance layer for agentic AI deployments in regulated industry. Based on these signals, a plausible trajectory is that NIST, CISA, or equivalent bodies begin drafting agentic AI security frameworks within 12 to 18 months that effectively mandate infrastructure layer controls of this type, particularly for AI agents with access to production systems or sensitive data. The $104 million cross-industry defensive initiative suggests the institutional momentum for standardization is already, and this is the important caveat. The gap between industry initiative and enforceable standard is historically wide and unpredictable. We've seen this pattern before with cloud security, with IoT security. The standard arrives years after.
In that lag, 18 to 36 months between capability jump and institutional response, that's where the real exposure is. So what should listeners actually do with this? Like, if you're a security engineer, a developer, a CISO, what's the actionable takeaway from everything we've discussed today?
A few things. First, if you're in security, look up the IronCurtain project on GitHub. Niels Provost released it as open source. And even if it's early-stage research, the architecture is worth studying as a design pattern. Look up Xfire too. Second, take the vibe coding risk seriously in your code review processes right now, before any regulatory framework mandates it. Treat AI-generated code the way you'd treat code from an external contributor you don't fully trust, which means actually reviewing it, not just running it and checking if it works. Third, the Mythos findings are worth reading about in depth. The specific detail about chaining 3 to 5 vulnerabilities into working exploit sequences at a 72.4% success rate. That's the number that should reframe how you think about your threat model for legacy code bases. And fourth, and this is the one I'd emphasize most, start thinking about the asymmetric guardrail problem as a policy issue, not just a technical one. The friction that AI safety measures impose on legitimate defenders is a real cost that needs to be part of the conversation about how these models get tuned.
So, let me try to pull the arc together here, because I think what we've covered today is actually a set of interlocking dynamics that each reinforce the others. We started with a 27-year-old bug found by AI for $20,000, which sounds like a cool research result until you follow the cost curve. Then we looked at why the economics of vulnerability discovery are fundamentally changing, not just incrementally improving. We went into the TCP SACK mechanics to understand why this class of bug is genuinely hard for humans, and apparently not that hard for AI at scale. We covered IronCurtain as an example of the right defensive philosophy, treating the LLM as an untrusted component rather than trying to align it into safety. And we landed on vibe coding as the feedback loop that makes all of this compound over time.
And I think the thing listeners should walk away with, the thing that I keep coming back to, is that this isn't a story about AI being dangerous in some abstract science fiction sense. It's a story about economics and asymmetry. The asymmetry between offense and defense has always existed in security. What's changing is the rate at which AI is tilting that asymmetry, and the speed at which the cost of offensive capability is falling. 20,000 zero day is a 1,000 zero day is democracy. And the codebases that those future 0 days will live in are being written right now. partly by AI assistants that don't fully understand the security implications of the code they're generating. The people building the right responses, the Niels Provises of the world, the teams behind initiatives like the $104 million defensive fund, they're not wrong about the direction. The question is whether they're moving fast. And based on how quickly Mythos' capabilities jumped from near zero to 72.4% exploit success, I'm not sure anyone can answer that confidently yet.